Welcome everybody, it's Ramchandra from Civil Mech Maths Concepts. In this video, I explain the properties of the fluids. It's for SSC JE, GATE and UPSC examinations, Fluid Mechanics, first lecture. Please listen to this. Welcome everybody, it's Ramchandra again from Civil Mech Maths Concepts. For SSC JE examination, for civil and mechanical engineering graduates and diploma holders. In this examination, fluid mechanics is the common subject, and this is the lecture number 1 on fluid mechanics, and I had already given certain MCQs and also brief about the examination in my previous videos. Now the main course starts from now on. I have taken fluid mechanics as the first chapter and first subject to start with, because it is a common subject between civil and mechanical engineers. And this particular subject, whatever my lecture, it includes both paper 1 and paper 2 syllabus, and also it is useful for both civil and mechanical engineers, and also it covers the total syllabus of civil and mechanical engineers JEE, JE, SSC examination, and also these lectures can be referred by GATE aspirants also. Best of luck to everybody. Please listen to my lecture, and in this lecture I am going to explain the definitions and properties. The definitions and properties are very important, and they are very useful for understanding the typical problems being given in the examination point of view. If your definitions and properties are understood very well, the concepts can be established from them and the subject can be understood very easily. The definitions and properties is one of the most important chapters. Then I'll spend more time on these definitions and properties. Please listen to this lecture till the end, and please review and comment for improvements. And if you feel this lecture is good, then you can plan to continue the lectures with me by subscribing, and regular updates will be sent to you on the lectures being given on this subject. First, let us start with some definitions, like what is a matter? Matter in the universe, it consists of solids, liquids and gases. Solids, liquids and gases, these are all depends upon the crystalline structure. Crystalline structure, and solids have a compact crystalline structure where it will be difficult for us to deform under ordinary forces. Whereas liquids and gases, they have a loose structure. I can say the amount of molecules in a particular structural arrangements are lesser or less compact in liquids when compared with solids, and the compactness in gases is still further reduced. That means liquids and gases, they are affected by the small forces that are applied on them, as the structure is not very compact. And these liquids and gases, when are applied by small forces like a shear force, then they continuously start deforming. That property is the most important property which defines or which distinguishes a fluid and a solid matter. A fluid is a liquid or gas. It can be either liquid or gas. A fluid is either a liquid or a gas. Please remember, gas is also a fluid. Liquid is also a fluid. A matter when exists in gas or liquid form, then that is called as a fluid. Almost major portion of our human body is in liquid form. Blood is a liquid. These are all fluids. And more than 70% of the universe is full of liquids. And the atmosphere around us is full of gases, which are also fluids. Air is also a fluid. Please remember, air is also a fluid. Water is also a fluid. Liquids and gases are fluids in the matter. Out of solid, liquid and gas, liquids and gases are fluids, and out of that liquids and gases, a major portion of our universe and body is made of the fluids, and fluid has a particular character. It deforms continuously under shear force, how small it may be, as long as the shear force applied. As long as the shear force applied. Let us take, for example, let us take a solid block here, and you apply a shear force. Shear force is a lateral force. It's not a force perpendicular to the cross sectional area. It is a shear force you are applying. This block may not easily get deformed. For small shear forces, the shape of the block will be same. Tau is the shear force. Tau is the symbol used for shear force. And when shear force is applied on the surface of the solid block, for small values of tau, there will not be any deformation, apparent deformation. Tau is small, apparent deformation is 0. We will not be able to visualize it except under high precision microscopes. That will be engineering, from engineering point of view, for all practical purposes, that can be neglected. If it is a liquid flowing in a pipeline, a small shear force will make a liquid point A here, and this moves to A dash here from A. This is dx, this is y, or dy you can call. That means sorry, this is dx dy. Now you just see a small amount of shear force when applied to a liquid, then it deforms, that starts moving. Liquid starts moving from A to A dash, whereas solid particle here A, it remains at A only, whereas a particle at A moves to A dash. From A to A dash by the application of a small shear force also. This is called as deforms continuously under shear force, how small it may be, as long as the shear force is applied. In a stationary pond, you have thrown a stone and that stone moves parallelly. Let us say you have thrown a stone parallel and it touched the surface of the pond, and in the pond there will be ripples, waves. There is a pond here, water is still, water is not moving. Initial condition, you have thrown a, water is up to this level, top level. You have thrown a stone from here, it touches, it moves in this way, stone moves in this way. Please listen, this type of explanation will not be there in any textbook. Stone, this will not be there in any textbook. Please listen to me carefully. Try to understand this. Shear force is very, very important in fluid mechanics. What happens? This particular, it touches, the stone touches point A and it moves further. What happens? Whatever the particle here, A, there will be ripples in the pond and this particle moves from A to A dash. Just see. A to A dash it moves. And this is dy. For a depth also there will be movement of the particle. I am simplifying and explaining you so that you will understand the meaning of the shear force. That means laterally the water moves. You keep a small ship made by small ship, you make the toys, ship toy made by a paper, or you just make a paper to be there on the top of the pond, a small paper, light paper, and you throw a stone. Then that light paper moves from A to A dash, and it also causes a movement in the vertical direction and also horizontal direction. The movement will be like this. Please, this is the main surface. The movement, crust, trough, crust, trough, crust, trough. Like this movement will be there. That is caused by the shear force caused due to the what you call stone thrown. That stone thrown causes both horizontal and also vertical forces. Here it is the stone thrown. Stone is not going to hit exactly parallel to the surface. It will hit at a angle theta, and this is the velocity of the stone. This velocity will have a horizontal component Vx and a vertical component Vy. Due to this horizontal component and vertical component of the velocity, velocity is nothing but force. Of this, there will be vertical movement of the paper, light paper, which was previously at rest, horizontally and vertically also. Please try to understand. And this is due to the vertical forces caused and horizontal forces caused. Horizontal forces are shear force. Vertical force is our normal force. Then you try to understand this now. horizontal force as long as it is applied, or a shear force as long as it is applied. Horizontal means don't take it as a horizontal only, it is only for your convenience I am telling, parallel to the surface. When a force is applied parallel to the surface, it is a shear force. Perpendicular to the surface, it is called as normal force. Now, this liquid or gas deforms continuously as long as the shear force is applied. Once it deforms, what happens? There will be a lot of dynamics involved in the fluid mechanics. For example, let us sit in an aeroplane. Aeroplane is moving in air. Aeroplane is like this. Airfoil or aeroplane made of airfoil. Now it is moving this way in this direction V. This air is surrounded by it. These explanations will not be available anywhere. Air is surrounded. Air is a fluid. Here, due to the velocity of the aeroplane, there is a force applied. I told you, velocity is nothing but a force. Force applied. When force is applied on the air, there will be deformation. What is the deformation? What shape of the deformation? Depending upon the shape of the aeroplane. There will be deformation in the air. That means air will not be same in the same condition as it was previously when it was still. When there is no aeroplane moving in the sky. When airplane moves in the sky, it exerts a force on the air and it causes turbulence in the air, and air moves get dispersed here and there, and this is what is a deformation. The surfaces of the air packets, this is the original surface, then it moves in this direction. The surface can be like this, it moves. Like this, air pockets gets dispersed. That's what is deformation. Just see here in this liquid also, we have shown dx and dy. Now, this deformation continues as long as shear force is applied, and how small it can be. Need not be very big shear force. A small shear force can also cause deformation in liquids and gases, whereas infinitesimally small shear forces will not cause noticeable deformation for solids. That is the difference between fluid and solids. Now, let us see. Is there any relation between shear force or shear stress and velocity gradient? You see, a particle is moving with a velocity v. It causes a deformation. The velocity gradient this is for a distance of dy, let us say. Instead of x, we will say it as dv. The velocity gradient, velocity is, let us say, u or v. These are all only symbols, and also they are only what you call nomenclature. Don't worry about u and v. There is a relation For shear stress, there is a relation for shear stress of any fluid moving with a velocity of u and the particle moves from A to A dash. This du by change in velocity by change in the depth. The particle is there. This is the velocity. Du by dy is equal to velocity gradient. What is velocity gradient? I told you in the first class itself. A gradient is the quantity with respect to some space quantity. Change in the original quantity, ratio of change in the original quantity to the change in the space quantity, positional quantity, not time. Rate is with respect to time, whereas gradient is with respect to position. Du by dy is equal to velocity gradient. For example, in a pipeline, this is the center line velocity and this is the velocity and position A to A dash. This is, you can say, V dash, and this position here velocity will be maximum, and the position, as long as this is the velocity profile, and change in velocity dv, and change in depth, change in velocity divided by change in depth. For example, you try to understand this with example, real example. I have a pipeline here. Why I am explaining in detail these definitions, I can read out and go up. No, I am not interested in that. I want to explain you fully. This is the velocity with which fluid is moving in a pipeline. The velocity profile will be parabolic profile. This is V max, center line velocity. This will be maximum here. And as you go, this is the R, radius of the pipe, and this is D, the diameter of the pipe. As you move from top up to center, here it is maximum, V max. And from here to here, when you change Y means it is changing. It can change up to R. When you change, this is Y, then this is dy. Let us say it is another point, it is another point. This is this, whatever shape is there in this shape, it is the dv change, and this vertical distance, it is dy. This dv by dy, please try to understand geometrically. This change in velocity in the parabolic portion, change in velocity in the parabolic portion is dv. Vertical portion distance is dy. This dv by dy is equal to velocity gradient. In mathematics, what is dv? dv is very small, infinitesimal change. When you read your, go back to your limits and derivatives in your class 10th or class 11th studies, or your diploma in engineering first year mathematics courses, or engineering mathematics courses in your graduate engineering, you know that whenever there is a differentiation, this differentiation talks about the infinitesimal changes. That means this dv is very small, dy is very small, dv by dy is equal to velocity gradient. Please try to understand. This velocity gradient, there is a Newton law in which shear stress is directly proportional to velocity gradient. This is the Newton's law. That there is a, whenever something is proportional to something means there is a constant. Constant of proportionality should be introduced. That constant of proportionality is mu. Mu into du by dy. This is Newton's law. Whenever there is a fluid which follows this Newton's law, that is called as Newtonian fluid. You just see a matter is composed of solids, liquids and gases on the basis of the crystalline structure and compactness of the molecules. We can define solids and liquids and gases. Mainly, we will define in engineering practical point of view as a solid as a matter in which a small shear force doesn't make a visible or apparent practically relevant deformation, whereas for liquids and gases, a small, how small it may be, a small shear force will cause the liquids and gases to deform continuously as long as the shear force is applied, how small it may be. Then there is a concept called velocity gradient, and that velocity gradient is du by dy, change in velocity with respect to change in position. dy is change in position, du is change in property. Change in velocity divided by change in position dy is equal to velocity gradient. As per Newton's law, it is shear stress is directly proportional to velocity gradient du by dy, which is a constant of proportionality is introduced by Newton. It is called as mu, which is nothing but viscosity. I will come to viscosity in the next definition. Now, let us talk about non-Newtonian fluids. Non-Newtonian fluids are the fluids which do not obey the Newton's law. Which do not obey the Newton's law. Now, let us take any fluid. There can be any fluid here, Newtonian, non-Newtonian. There should be something we can call, some rule should be governing them, their movement. Then that equation for shear stress is, shear stress tau is equal to m into du by dy to the power of n. This is the general equation. Please remember this general equation. If n is equal to 1, Newtonian fluid, n is not equal to 1, non-Newtonian fluid. In this equation, tau is equal to m into du by dy to the power of n. Tau is equal to m into du by dy to the power of n. In this, if n is equal to 1, then Newtonian fluid. If n is not equal to 1, then non-Newtonian fluid. What is m? M is a constant of proportionality, which is nothing but mu. That is viscosity. I think these you might have understood the definitions. Now, let us go to further definitions. Now, what we have spoken till now was about the matter and what matter is of how many types and what type of what is a shear force and how shear force is related to velocity gradient, how fluids are classified, what are the fluids, gases and also liquids are fluids, and how fluids are classified as Newtonian fluids and non-Newtonian fluids. Now next comes, a fluid is there. It is governed by what type of properties? Fluid will have a property. The first property which governs the fluid is density. Density is equal to mass by volume. The mass of the fluid per unit volume. The mass is in kg. We will be dealing with SI units only because it is given that in our syllabus we will be dealing with SI units. In the examination of either GATE or in the examination of UPSC or in the examination of SSC JE, we will be dealing with SI units. If you want a conversion from SI units to other units, you can definitely refer to standard books, but however, I will be dealing with SI units only. And there are dimensions, main will be MLT, quantities. M is mass, length, time. Mass is in kg, length is in meter, time is in seconds. Standard units of a SI unit. Now density mass by volume. Mass is M. Volume is L into L into L. L cube. M by L cube. This will be M to the power of 1, L to the power of minus 3, T to the power of 0. From your regular dimensions which you have learnt in your elementary physics. Then density is M, L to the power of minus 3, T to the power of 0. What is M in SI units? kg. L cube is cubic meter. And there will be definite temperature and laboratory conditions, atmospheric pressure, temperature. These are the conditions under which different fluids, temperature usually will be 20 degrees centigrade, laboratory conditions, and pressure approximately 1 atmosphere. Under 1 atmospheric pressure and temperature of 20 degrees centigrade, the densities of the different products are found out. Now you tell me, what will be the density, order of the densities of solid, liquids and gases? The density of solids will be the highest because they have a compact structure, and the density of liquids will be lesser than the solids, and the density of the gases will be the least. This density is denoted by called rho. This is called as rho or HO. The symbol rho or HO, rho. This is rho of solids is greater than rho of liquids is greater than rho of air. Air or gas. Now, the standard value of rho of water is 1000 kg per cubic meter. It can also be taken as row of water. Some books they may take it as 998 kg per cubic meter. The row of air will be 1.205. Please remember these values. How much difference? Almost air, water is 800 times dense than air. These values, standard values, you can get even from your textbooks, but however I have given, because we will be dealing mainly with water and air in our syllabus. Now, there are certain quantities called specific. What is specific? Specific value, a specific quantity is called as per kg of a matter. What is that quantity? Specific always deals with per kg. Per unit mass we can say. Specific heat is kilojoules per kg. Specific volume per kg. Specific energy per kg. What is that? Specific deals with per unit mass. Specific heat will be heat per kg. We are talking about SI units. Specific energy is equal to energy per kg. Specific enthalpy is equal to enthalpy per kg. Similarly, specific volume. You tell me specific volume is equal to volume per kg. That is equal to cubic meter per kg, which is nothing but 1 by rho. 1 by density is equal to specific volume. This is also very, very important. It should be understood. Whatever I am discussing here, these properties, these are definitions, are to be understood clearly. Next, what is specific weight? Here, weight per unit volume. Density is mass per unit volume. Gamma is equal to weight per unit volume. Weight is in newtons. Volume is in cubic meter. What is weight? Weight is equal to mass into acceleration due to gravity. Here don't confuse with this specific to this specific. This is different. Weight is equal to mass into acceleration due to gravity. And gamma is equal to weight mg by volume. That is equal to m by volume into g. That means gamma is equal to rho into g. This is very, 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 very important. Equation, very, very important equation. And gamma is equal to rho g. Gamma sometimes is also called as W. Sometimes in some books it is called as W also. Gamma is equal to rho g. Now, let us talk about the relative density. I will talk about the specific weight maybe in the next definitions which follow. Relative density. What is relative density? Density of some fluid divided by density of water. A relative density of a liquid is, when you take the liquid, it will be density of that liquid divided by density of water. Very, very important. Similarly, relative density of gas will be a particular gas, it will be relative density of gas by density of air. Now let us say, what is the relative density of diesel? You know diesel is a liquid. You go to a petrol pump, put petrol or diesel in your car or in the vehicle, then relative density of diesel is equal to density of diesel. If you see in the petrol pump, you will see that density is written there. Density of diesel by rho of water. What is the density of diesel? 850 approximately kg per cubic meter. What is the density of water? 1000 kg per cubic meter. What is the relative density of diesel? It will be 0.850. Similarly, for different liquids, why I have taken petrol or diesel? The reason being that you regularly go to a petrol pump and take your product. That is a practical engineering example. Similarly, for a gas also, you use cooking gas, LPG. You know, density of LPG gas you can get, and density of air is known, then relative density, it will be in the range of around 0.4. You can check up, it may be. And like this, relative density of a particular product, fluid, can be easily found out. This is the definition of the relative density. Whatever definitions I am giving here, they are all very, very important definitions. Don't neglect them. Next comes the pressure. What is pressure? Pressure is equal to force per unit area. Force exerted per unit area. Force, this here force is normal to the area of the action. For example, there is one circle is there. Here there is a point A, and this is the center O. Force is applied like this. Force. This portion is the area on which force is acting, and this force should be normal to the area of action. Force should be normal to the area of action. This is very important. Please remember this. P is equal to pressure. Force normal to the area of cross section on which it is working on. Then this is the dF. This we can say dF. And this is dA. dF by dA when you take the small quantities. When you take like this, pressure can be, this is the force, this is the area of cross section on which force is acting. The both should be at 90 degree angle. Normal force divided by area of cross section on which it is acting. For example, force is this way, then area of cross section we cannot take. In the previous example, where force is normal. We should convert the force into xy or xy components. In this case, what happens? There will be some fx, there will be some fy. For finding the pressure, normal pressure, here normal force by area of cross section. Shear stress fx relates to the shear stress, fy relates to the normal pressure. Please try to understand. If force is given at an angle theta, then that force is to be decomposed into horizontal force and vertical force, and where you wanted to find out the area of cross section, a normal force divided by the area of cross section will give the pressure, whereas shear stress is given in the direction of the horizontal force, horizontal or x direction, whatever we call. Please understand. And force is, I have already told you, force is equal to mg, kg into m is meter per second square. This we will call it as a Newton. This is Newton. And area is square meter because we are using SI units. And Newton per square meter, this is called as Pascal. This is the SI unit. Please be very, very sensitive, very, very careful in understanding the units of the pressure, units of dynamic viscosity, units of force, units of length, units of volume, which may look very simple, but they get complicated once you go deep into the subject. Don't club two types of units. Follow one unit system throughout the subject. You follow that system SI units, and you ensure that your answer will be in SI units. If you want to convert into as per the questions given, you can convert, but SI units is the system which we regularly follow in our engineering subjects. Even in SSC, I think JE, in the advertisement they have given, they will follow SI units. Please cross check. Let's follow SI units only. Now pressure is there. We are all under the influence of certain pressure. That is called as atmospheric pressure. At a sea level, mean sea level, MSL, there is an atmosphere above earth. There is an atmosphere. That atmosphere is full of gases. Definitely a gas is a fluid. A fluid bound to exert pressure. A fluid is bound to exert pressure. And at normal conditions, at normal mean sea level, the pressure exerted by atmosphere on the surface of the earth, I am not talking about inside of the earth, on the surface of the earth at mean sea level, that pressure is called as atmospheric pressure. Pressure exerted by one atmosphere. Because there can't be 10 atmospheres until and unless we develop a pressured conditions in the laboratory. The pressure on the surface of the earth will be at mean sea level. At different places it will be atmospheric pressure, and it will be different at different places because of the altitude, and the average value is taken as 101.325. Please remember this, 101.325 kilopascals. What is kilopascals? 101.325 into 10 cube. What is kilo? If it is some unit is there, it is 1. Then 10 cube is equal to kilo. 10 to the power of 6 is equal to million. 10 to the power of minus 3 is milli. Like this whatever values are there, you can get from your elementary physics classes. And 101.325 kilopascal is 101.325 into 10 cube pascals. Then 1 atmosphere is equal to 1.01325 into 10 to the power of 5 pascals also. In this way also we can write. If you want to remove kilopascal. This and this are same. Because 101.325 is 1.01325 into 10 square. 10 square into 10 cube is equal to 10 to the power of 5. Now, the pressure can be expressed in the head of the fluid also, as the head of the fluid also. For example, I have a fluid column or one, what you call a tumbler having a height h, filled with height h, water filled with, and kept on the table. Whatever may be the height of the tumbler, when we neglect the weight of the tumbler, then what will be the pressure exerted by this water column on table? Above the water column, the pressure will be normal, that is P atmosphere, depending upon the altitude where we are conducting the experiment, that is P atmosphere, which is nothing but 1.01325 into 10 to the power of kPa in normal conditions. This is P atmosphere. And this is the point A, where above A there is no water column. Here it is a fluid, water, let us say water or fluid, we can say, has a height of h. This is the point B. At Pa is equal to P atmosphere. You agree? Because it is only atmospheric pressure which is acting on the water surface, nothing else. At Pb, P atmosphere plus pressure due to water column. Please try to understand. Whenever pressure is calculated, it is called as a difference in pressure, because we can't directly calculate the pressure. Difference in pressure. Delta P. Please try to remember this one. It's very, very important. We will calculate through our instruments only delta P. Delta P is equal to Pb minus Pa. Correct? The pressure due to water column is equal to Pb minus Pa. That is equal to Pb is P atmosphere plus P water column plus P atmosphere minus Pa, sorry. Water column minus P atmosphere. Then, when you measure the pressure with any instrument, the water column pressure is equal to delta P is equal to P water column. The P water column pressure is for a height of h, the water column pressure is equal to rho GH. Rho G I have already shown you. What is the unit of rho G? Mass by volume, Newton per square meter. This is equal to Newton per cubic meter into H is in meter, that is equal to Newton per square meter, that is in pascals. We have cross-checked the units also. The pressure due to a water column H is, or a fluid column, let us say, not water, is rho GH. If water is used as a fluid, then for this 101.325 kPa, you just see the magic. 101.325 kPa is the pressure. That is equal to, what is rho? 1000. What is G? 9.81. What is H of water is not known. Everything in SI units. Now, what will be height of water for 1 atmospheric pressure? 101.325, we can convert it as 101.325 into 10 cube divided by 1000 into 9.81. That is the water. Everything is in SI units. 101.325 into 1000 divided by 1000 divided by 9.81. That is equal to 10.33 meters. This is what is exactly 10.336 meters of water. When you want to convert one atmospheric pressure into pressure head units, pressure can be expressed either in pascals or in pressure head. Because how it can be in pressure heads? Because rho is constant and G is constant, and both are constants, we can convert into pressure head. When we convert into pressure head, this will be .336 meter of water, if water is used. Because water columns will be very high. For 1 atmospheric pressure itself, we require 10 meters height of water column. 10 meters is approximately 30 feet, more than 30 feet. It is 3-story building height, more than 3-story building height. Water column we have to construct for finding the 1 atmospheric pressure. For that, scientists have gone for a better fluids, and one of the fluids is found to be mercury. Hg is mercury. Instead of water, we can use mercury, where the relative density of mercury is equal to 13.6. That is equal to rho of mercury by rho of water. Now rho of mercury will be 13,600 kg per cubic meter. Now you find out the head of mercury. Head in mercury is equal to 101.325 into 10 cube from this formula divided by, rho is 13,600 into 9.81, which gives you 0.760 meter. This is nothing but 760 mmHg. Now, it is very, very, very important to understand the units of pressure. Very important. I took more time here. 1 atmosphere is equal to 101.325 kilopascals. That is equal to 101.325 into 1000 pascals. That is equal to 1.01325 into 10 to the power of 5 pascals. It should be in your mind. And if expressed in water column and mercury column, water column is 10.336 meters of water column pressure, 1 atmospheric, and 1 atmospheric in mercury column is 760 mmHg or 0.760 meters of mercury. Then there is a conceptual confusion between a bar and atmosphere. Atmospheric pressure is 101.325 kPa, whereas 1 bar is equal to 100 kPa. Please try to understand the difference between them. 1 bar is another unit. 1 bar is equal to 100 kPa. That's equal to 10 to the power of 5 Pa. Whereas 1 atmospheric pressure is equal to 101.325 kPa. If in the examination, to confuse people, if it is given that atmospheric pressure at a particular altitude is equal to 1 bar, means that you take it as 100 kPa. Don't take it as 101.325 kPa. Please differentiate between bar and atmosphere. Now, shear stress, I have already explained you. Shear stress tau is equal to m into du by dy to the power of n. When n is equal to 1, then this comes to this. This is Newtonian fluid. Types of fluids we will discuss in the next following classes. Next comes the lecture is a little bit long. Please bear with me. These are all very important concepts. Next comes viscosity. What is the definition of viscosity? Viscosity is the term used to understand the resistance to flow. Please, you take a pipe, a small pipe, a small tube rather, you pour water in it. When you pour water in it, the water comes out from the other end, a open tube. A open tube. Need not be horizontal, it can be inclined also. And you pour water in it. Water comes out. You find the time t. In how many seconds water is coming out, and here you find the quantity, some 100 ml you put, and you see that 100 ml in how much time. When you understand the concepts with experiments, then you will understand better. 100 ml is received in time some seconds, t1. Let it be inclined. Okay, inclined pipe. Same inclined pipe, you pour bituminous, tar. You know tar, bituminous, and it comes out. The black bituminous is being poured on the roads for making the roads. Tar roads we call. That's very thick. When you pour bituminous, 100 ml here also 100 ml received, Q. Then there will be time 2, T2, that you may find out the time. What happens? T1 is lesser than T2. The density of bituminous is greater than density of water. Relative density of bituminous will be greater than unity 1. Why it is taking more time? The reason is there is a resistance to flow for bituminous to freely flow in the pipe. That is called as the viscosity. The viscosity of bituminous is greater than the viscosity of water. Viscosity I have already defined. Where it is a mu, we call it as mu. Pronounce it as mu, mu. Mu is dynamic viscosity. That means the layers of thickness, the thickness between the layer to layer, bituminous, one layer is there, another layer is there, layer 1, layer 2, layer to layer. The resistive force is more in bituminous than water. Water flow is easier because layer to layer that resistance is there. The tension, the force between layer 1 and layer 2. This is what you call it as the 2. Shear force or shear stress. The layer to layer force, in between force, that resistive force is more in bituminous than water. Viscosity represents the resistance to flow. What is Newton's formula? Newton's formula is equal to tau is equal to mu into du by dy. Shear stress. Shear stress, if viscosity is more, tau is more. For the same du by dy. For the same velocity gradient, tau will be more when viscosity is more. Tau is nothing but shear stress, that is nothing but resistance to flow. Viscosity is resistance to flow. Shear stress means there will be more stress for the layer to move. Movement will not be that smooth. Whereas in water, tube movement will be very smooth. As a homework, I want you, please do this homework. Please do this homework for the benefit of all of you. Homework. List out mu values for at least 10 commonly used liquids, commonly used fluids rather. List out 10 the viscosity values for at least 10 commonly used fluids. I told you one is bituminous, another is diesel, commonly used, another is water, and you can say benzene, alcohol. You take out 10 products, 10 fluids, list out them in the descending order and try to understand why that particular viscosity is more for a particular fluid and why viscosity is less for a particular fluid. That is the internal resistance between the molecules. In the bituminous, the internal resistance between the layers of bituminous will be more. That means viscosity is more. It takes more time for the product to flow. And this time is nothing but per unit time. The units of this is nothing but per unit time. Du by dy is equal to meter by second by meter, that is equal to 1 by second, that is a second to the power of minus 1, t to the power of minus 1. Please try to understand velocity gradient. How beautiful, everything is internally connected. Just see. That means here t is more, 1 by t is less. That means velocity gradient for bituminous is less. Velocity gradient means the flow is less. Velocity is not there. Velocity gradient means velocity is not there. Flow is less. Here, you try to understand. T is more. My questions, MCQs will be depending upon this only, these concepts. They will not be from any regular textbook. You will find these things. Try to understand. Try to understand these 10 products. I will be giving the MCQs in the next lecture or other than next lecture. Once I complete my definitions and properties, I will give you huge number of MCQs on that. It's not going to be that easy. Please, I am not scaring. I want to make you prepared for your SSC examination or UPSC examination or GATE examination for fluid mechanics. I am making you alert. I am making you awake. Next, this mu is there. We have called it as a dynamic viscosity, and this dynamic viscosity is Pascal into second. Please tell me how dynamic viscosity can be Pascal into second. Can you please derive the units for it? We know that from Newton's law, tau is equal to mu into du by dy. Du by dy we already know per second. That is mu into per second. Tau is equal to Newton per square meter. That is equal to Pascal. Stress is pressure. Pressure is Pascal. Implies mu into per second is equal to Pascal. Implies mu by second is equal to Pascal. That implies mu is equal to Pascal into second. Everywhere I am using SI units only. Don't get confused. When you use the SI units, the units of dynamic viscosity is equal to Pascal into second. These things you should be able to derive them. This can also be written as Newton second by meter square. Newton by meter square into second. That is Newton second by meter square. This way. You should be able to derive. On this also I am going to give some MCQs. And the practical value of a dynamic viscosity is mentioned by the manufacturers for a fluid whenever they design the engineering. For engineering designs, we will use usually the dynamic viscosity in poise. And whenever you go and stand, tar road is laid in your village or town or city, the bituminous is heated. What is the reason? It is heated so that bituminous flows freely or easily. For easy workability, the bituminous is heated. What happens to the viscosity of the bituminous? When viscosity means resistance to flow. Resistance to flow will be decreased. That means keep bituminous in mind. For liquids, mu decreases with increase in temperature. Very, very, very important conclusion. Whereas in case of gases, mu increases with increase in temperature. It's also very, very important conclusion. These two conclusions, why it is so, it is your homework. Please try to find why In gases, mu increases with increase in temperature, whereas in bituminous and other products we have seen with our own eyes from our childhood experiences that whenever tar road is led, bituminous is heated so that there will be easy flowability or easy workability. That means viscosity decreased. Viscosity is decreased with the increase in temperature. Resistance to flow is decreased. Flowability is increased. Whereas in gases, mu increases with increase in temperature. Please give me some examples. Give examples. At least 10 examples in gases also. Now, kinematic viscosity. Dynamic viscosity is used in Newton's law. Please, Newton's law, whatever viscosity is used, that is a dynamic viscosity. Tau is equal to mu into du by dy. Tau is equal to mu into du by dy. Tau is equal to mu into du by dy. Mu is dynamic viscosity is measured as a resistance to flow in units called Pascal second. And for liquids, mu decreases with increase in temperature. For gases, mu increases with increase in temperature. Next comes, there is another word called as kinematic viscosity. Kinematic viscosity is nothing but dynamic viscosity by density. Dynamic viscosity by density. Now, we will derive the units of kinematic viscosity. It is called as nu. Spelled as nu. Nu is equal to mu by rho. What is mu? Newton second by meter square. 1 by rho is kg, 1 by kg per cubic meter. That is equal to Newton is kg meter per second square mg into second divided by meter square into meter cube by kg. This kg will go off. Meter square will go off with 1. Meter into meter is equal to meter square. The second will go off. Then this will be, left will be meters by second. The kinematic viscosity units is meters square per second. Very important. And the practical unit is used as Stokes. 1 meter square per second is equal to 10,000 Stokes. Because the value, when it is expressed in meters per second, meter square per second, the values are very, very low. Hence, there is a unit called Stokes is used. The values are very, very high, meters square meter per second. Hence, there is a unit called, for practicability, Stokes is invented, and kinematic viscosity for practical purposes, it is used in practical industrial purpose or engineering purposes, mentioned as Stokes. 1 Stoke is equal to 10 to the power of minus 4 into meter square per second. Sometimes SI units may not be practical for use in the industry. Hence, some other derived units are used, and for kinematic viscosity, Stokes is used. For dynamic viscosity, Poise is used. Please remember this. They are not different from the SI units. They are only some ratio of the SI units. 1 Stokes is 1 by 10,000ths of the SI unit. 1 Poise is 1/10 of the SI unit. When you know the SI unit, you can know the Stokes. When you know the SI unit, you can know the Poise. This is how These are all the different definitions. It is only half done. In the next lecture, I will continue with the definitions and properties. It may be little longer, I may be taking little longer on this, but it's very, very important. Till now, what we have read is, we have defined what is matter, solids, liquids and gases, we have understood the difference. Then liquid, we said that it deforms continuously under shear force, how small the shear force may be as long as shear force is applied. Then we understood what is a Newtonian fluid and what is a non-Newtonian fluid. And then an equation is understood for any fluid, relation between the velocity gradient and shear stress. And we understood that when n is equal to 1, this is a Newtonian fluid, m is equal to mu, dynamic viscosity, that's a Newtonian equation. Then we went down to properties of the fluid. One is density and units of density and laboratory conditions for finding the density. Then inverse of the density as specific volume, cubic meter per kg. That values also we have got. And for water and air, next specific 8, that is gamma. Gamma is equal to W, it can be gamma is equal to rho g. And relative density, for a liquid it is rho of liquid by rho of water, dimensionless number. For example, we have done it for a diesel. And for relative density of gas is equal to rho of gas by rho of air, it is also dimensionless number. Then comes pressure. Pressure is normal force by cross-sectional area on which it is acting, and it can also be dF by dA, and units are Pascal, that is SI unit. The unit is called as Pascal, that is Newton per square meter. And atmospheric pressure, we have defined it as 101.325 kPa, that is 1.01325 into 10 to the power of 5 Pa, or 101.325 into 10 cube Pa. And when in liquid columns we measure it, that is equal to 10.336 meters of water and 760 mm of Hg, or 0.760 meters of Hg. Hg is mercury. And 1 bar is equal to 10 to the power of 5 Pa or 100 kPa, whereas 1 atmospheric pressure is 101.325 kPa. And pressure is measured as a difference of pressure because atmospheric pressure is always present. Then delta P between 2 points is equal to rho gh. From rho gh we can find out the height of the fluid column. The fluid can be mercury, fluid can be water, fluid can be anything. You take any fluid and find out the h as given in the examination using the rho gh formula. Then shear stress, Newtonian fluids we have defined. Then next comes, we have talked about viscosity, resistance to flow, and dynamic viscosity, and different units of dynamic viscosity, and variation with temperature. In liquids, mu decreases with increase in temperature. In gases, mu increases with increase in temperature. Next comes kinematic viscosity, the various units of kinematic viscosity and their derivation. And now, the most important thing is your homework. Please do your homework and comment and give me the list of the 10 normally used liquids for which you have noted down from standard books the dynamic viscosity and kinematic viscosity in SI units, in poise, and also in Stokes. And then another important is, in liquids you find out the variation of dynamic viscosity with respect to temperature. Take a particular liquid like water, something, and you find out for various temperatures from literature or from standard books how mu is varying. Similarly for gases, how mu is varying, and try to understand in gases why mu increases with increase in temperature. You take bituminous, for example, and you find out the mu, that is dynamic viscosity and kinematic viscosity with respect to temperature, and if possible draw a graph also. That is your homework. Homework is find the variation of dynamic viscosity and kinematic viscosity with respect to time. With respect to not time, with respect to temperature. Degree centigrade. Draw a table and draw a graph. This is question number 1. 2. Tabulate at least for 10 common fluids. Find out the values of dynamic viscosity and kinematic viscosity at standard temperature and pressure. Third, on Earth, the atmospheric pressure is equal to 101.325 kPa. On Moon, can you find atmospheric pressure? Please try. First 1 and 2, you should be able to do with whatever I have given the lecture. And third one, you please try. You can take Moon, Jupiter, Saturn. Try to find out. Is there any atmosphere on the particular planet? And what may be the atmospheric pressure on the surface of the planet, if atmosphere exists? These are the types of the questions which will give you insight and develop the interest in the subject. I am here interested to develop interest in you so that you will understand the subject, at the same time you feel comfortable to learn the subject. That's more important. And with this, I want to stop this lecture here, and in the next lecture I will be continuing with definitions and properties, very very important ones. Then again I will give you some homework. Afterwards, if definitions and properties are completed, then we will go for some MCQs on the following lecture. This way we will move forward. And my name is Ramchandra. I am an IIT alumni, and I wish that from my lectures you gain some insights and knowledge, and you improve your knowledge, work hard, and get better marks in your SSC JE, Civil and Mechanical Engineering, Fluid Mechanics subject. Best of luck to you. Please view my video. If you want further clarification, please comment. If you have any doubts, please comment. I will reply to the comments. Please review my video. Please comment on my video, and please subscribe to my channel to get the regular updates. And my channel is Civil Maths Concepts. This you can use in YouTube with a keyword by IIT Alumni also, to get access into my video easily. Civil Mech Maths Concepts is my channel name, and by IIT Alumni is a keyword you can use, and you can get into my video and you can view it repeatedly. You view it, understand it, and comment it. If you want any clarification, I will definitely do it. Best of luck to everybody. Thanks for viewing my video.